All right, so we're in Algebra 1, Lesson 8-4. Today's date is Monday, February 10th, 2020. Anyone want to read our objective? Yes, Wyatt?
Match exponential growth equation with its graph.
There it is. Notice I don't say graph an exponential equation. We could get there by today, but today's just that first little step of can you match one to another. So let's talk about where graphs come from. Generally speaking, they come from tables. So I have an equation here. My equation, again, whenever I have an f of x or a g of x or whatever of x, you can kind of cross that off. That's just function notation. Think of that as a y. Y equals 3 times 2 to the power of x. And I feel a little bit guilty because we skipped our unit on function notation, but it's just a fancy way of saying y equals. All right, so now you guys are gonna have to do some math with me. So if I'm plugging in values of x, let's say I plug in 0. 0 is gonna be plugged in right there. So you guys are gonna all shout this one out. Hopefully we can say it at the same time. 2 to the power of 0, anything to the power of 0 is 1. Good. And then 1 times 3 is
3.
All right, so it's 0, 3. And now a quiet raised hand to do the next one. Yeah, Charles, question.
So 0 to the power of 0 would still be 1.
Yeah, 0 to the power of 0. In order to answer that question, I have to teach you a little bit of calculus. It's undefined. You can't have 0 to the power. Well, yeah, it's undefined. There's a bunch of weird things that can happen, like infinity to the power of negative infinity. But yeah, once you talk about calculus, then we can have the tools to actually answer those questions. When I plug in 1, what y value or f of x value, what is our function? What is our height? When I plug in 1, it's going to be 2 to the power of 1. Think about what that is in your head. And then multiply that by 3, and you get what with a quiet raised hand? Someone has a card. Yeah, Esha.
6.
It is indeed 6, because 2 to the power of 1. Anything to the power of 1 is itself, so 2 to the power of 1 is 2. And 2 times 3 is 6. Perfect. I guess I can zoom in here. There's no need to have this zoomed so far out. And then when I plug in 2, an x value of 2, 2 to the power of 2. Okay, now times 3. Jade?
12.
It is indeed 12. What about the next number? And you don't actually have to plug in for this one. You guys can see the pattern now. We've talked about the pattern before. Oh, if I keep jumping on the table, if I'm doing the same pattern repeatedly as an exponential function, I should be able to say, oh, it's 3 comma something. So when I plug in 3, I get what out? Larissa?
15.
Be careful there. All right, Larissa. So when I plug in 3, I get
6.
Careful there. So notice the pattern. 3 goes to 6, goes to 12, goes to what? Not quite. To get from 3 to 6, you can either add 3, and if I go from 6 to 12, I add 6. Okay, that doesn't make sense. It's not a linear function. What if I instead multiply by 2? 3 times 2 is 6. Oh, times 2 again to get 12. Therefore, I should get...
15. So 12 times 2.
Keep multiplying by 2, exactly. Thank you, Asha. And I'll get... double 12. 24, yeah, nice.
Goodbye.
Yeah, question, Asha.
So why didn't the 3 imply the same way that we did the other ones? Because why?
Why didn't the 3 imply...
Like, so we put 2 as the form of x, but we didn't do that for 3, because if we did, 24 would be 18. So why didn't we do that?
It would be 18. I'm trying to...
No, because 2 times 2 times 2 is 6, right?
That's 2 plus 2 plus 6.
4 times 12. So 8, okay, never mind. Wait, okay, never mind. Because, yeah, never mind.
Okay. One kind of cool thing to point out on this table is this rule that we're having here on the side, times 2. Does anyone see where that's coming from in our equation? Yeah, Charles?
The power, so the factor.
Yeah, so it's this thing is called the base or the factor. So we can say that's the factor we've been calling him. You can think of this in terms of the base number. So the base number is always going to be the thing that you multiply by in the table, and that's going to be a really nice shortcut for us in the future. And then we'll see some other patterns start to emerge. What happens if I do negative powers? We've talked about negatives just a little bit. Whenever I have anything, I'll do the general rule off to the side. If I have like x to the negative 3, or even better than x to the negative 3, I'll say like, I don't know, let's say 3 to the power of negative 2. Does anyone know what happens when you have negative powers? One person remembers? One person knows? Yeah, Charles?
It would be 1 over 3 power 2.
Exactly.
Oh,
Yeah. Yeah, so whenever I have a negative power, I have to come back here and say, oh, this is really 3 over 1, and then I take the reciprocal and I make it a positive power. Yeah, thank you, Charles. So that's what I'm going to have to do now back over here. If I have negative 1 being plugged in for this value of x, this is now going to be 2 to the power of not x, but negative 1. I'm going to have to flip it. So let's do our scratch work off to the side. If I have 2 to the power of negative 1, it's going to equal 1 over something, something, and then I'm going to have to multiply by 3. What should that value be? So if I plug in negative 1 for x, what should my y value be? What should my function's height be? The quiet raise hand. Does anyone still have their card? I'll help you guys walk through it too if you want some help. Hugo? So if I have 2 to the power of negative 1, it's equal to what fraction? 1 over 2 to the power of 1. Perfect. And 1 over 2 to the power of 1 is just what normal fraction with no powers? So anything to the power of 1 is itself, so you can kind of cross off the 1 and it turns into 2? Yeah, exactly. 2 on the bottom, so 1/2. So that means that this part right here is 1/2, and then I have to multiply by 3. What's 3 times 1/2? And I can give you a hint here too.
1.5.
So if I do 3 times 1/2, that's 3 over 1 times 1 over 2. I just multiply the tops. Go for it, Hugo.
3 over 2.
Yeah, 3 over 2. Or 1.5. Either way is fine. I like 3 over 2. I like fractions more than I do like decimals because it's easier to see the pattern. Yeah, thank you, Hugo.
Why isn't it just 1 over 2?
Why is it not 1 over 2? Because we have to multiply by this original 3 up front as well.
Oh.
Yeah. And I'm kind of regretting adding the table the way I did. This negative 1 should really be above the 0, and this negative 2 should really be above the negative 1 in order to see the pattern. Because if I want to go backwards now on my table, if I want to go from this 3 value up, instead of multiply by 2, I'm going to be dividing by 2. And hey, 3 divided by 2 is 3 divided by 2. Which means if I want to go from negative 1 to negative 2, again, I should be dividing by 2. It's weird because I'm going the wrong direction. I should be fixing this table. But if I do 3 halves and I divide by 2 again, what should my fraction be? Jade?
6 halves?
Ooh, good guess. I'm dividing by 2. You multiply by 2.
Oh.
So add a 2 to the denominator instead of the numerator. I multiply the denominator by 2. Yeah, Jade? 3/4, yeah. So I keep multiplying this denominator by 2, and that's how you get those fractions. All right, so that's where the table comes from. I'm assuming that everyone, if you had enough time now, you could rederive this table and then graph this again. But I need to make this shorter. I need to show you the patterns. That way you don't have to use a table. So coming back over here, we're going to graph every single one of these points. So the first point I'm going to graph is 0, 3. So 0 in the x, 3 in the y. There's the point right there, 0, 3. Graph 1, 6. Graph 2, 12. 3, 24. Negative 1, 3 halves. You're going to have to kind of guesstimate what that is. Negative 1 and 3 halves. Well, I can say that's right about there. And negative 2, 3/4 is that's right about there. All right, so everyone has these points down on their graph, correct? Good. All right, now we're going to connect them with a line that is slightly curvy-ish. Don't connect them with just straight lines. Try to make it slightly curved. It's going to come through these points. I find that it helps if you just, I don't know, I'm not the best artist, but whenever I'm doing graphs that have curves, if I do a bunch of quick little lines and I draw like a bunch of little lines in between the dots instead of one held down line, it makes it look a little bit nicer. You might disagree, but that's my strategy. And then we don't end at this point 3, 24. It keeps going. So it keeps going up and up and up. So I'll do an arrow on the top right saying, hey, I continue on and on and on in that direction. And I go on and on to infinity really, really fast. This is getting faster and faster and faster. Yeah, question, Charles.
So if it kept on going, would the line eventually like curve around?
That's a good question. What do you guys think?
I think, no, I think it's just,
They just broke the sound barrier.
yeah, it just stay really super close, like way too close.
So the answer is no, it never comes around. There's two reasons for that. The first reason is if I ever have a function that looks like this, or a function that looks like that, they're not technically functions on the Cartesian plane because they don't pass the vertical line test. The vertical line test says if I draw any vertical line anywhere through the function, I'm only allowed to touch it once. So if I touch it more than once right here, then that's not a function. Of course, I'll teach you how to break that rule once you get higher levels of math. But yeah, rules are always meant to be broken. That's kind of a general theme in mathematics. It's like, you can't have negative amounts of apples. Well, I'm going to invent negative numbers. Well, you're not allowed to have square roots of negatives then. It's like, I'm going to invent imaginary numbers. So if someone tells you you can't do something, you just go ahead and do it. That's kind of the fun thing about math. Other thing, oh yeah, so what's happening on the left-hand side? Does anyone have an idea of what's going on? Yeah, Eamon.
The value is constantly being cut in half.
Cut in half. Yeah. So if it's being cut in half, will I ever cross past this x-axis and come down here?
No.
No. So what we need to do now is we need to make a line that gets closer and closer to this x-axis without ever touching. So it gets closer and closer, half and half and half and half. Oop, I don't come back up. Half and half and half. It gets really, 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 really close to the x-axis, but it never ever touches. You're not allowed to touch because if you touched it, that would mean that your y value was 0. If this y value right here was 0 and you try to solve this, you can't solve it because 0 is equal to 3 times whatever, divide both sides by 3. So how can I have 0 is equal to 2 to the power of something? No matter what value I put in for x, I will never be able to get 0. You can try negative a billion. Your calculator will round to 0, but it will be really, really close to 0. All right, so there is your graph of an exponential function. It continues going on to the right forever and ever. So the domain of this function is from negative infinity to infinity. I'll write it down here. It's not going to be tested or anything, but it's handy to know the domain. What are you allowed to plug in for the x values? If you forgot what the domain is. So the domain is x values. The domain is all the way from negative infinity all the way to positive infinity. I'm allowed to go anywhere in terms of left and right. There's no restriction on how far left and how far right. Of course, if I go right to 1,000, my height is going to be astronomically big, like so big I can't even comprehend that number because this is growing so fast. If I went really, really far right, it'd be up in the heavens. What about the range? How far up and down can you go? So the domain, I'm going to draw arrows to help you remember. Domain is left and right. What about up and down? So the range, the y values. How far up and down am I allowed to go? Well, clearly this arrow, what happened there? This arrow right here goes up and up and up forever to infinity, so it definitely has an upper bound of positive infinity, but I'm not allowed to go negatives. In fact, I can't even be 0, so I say from 0, not including 0, all the way to infinity. So this is not a square bracket. Square bracket means I can be equal to 0. This parenthesis here means that I get close to 0 without actually touching 0. So the range of y values, another way of saying that is, hey, keep it positive, then you're good. General life rule there too. If you guys just keep it positive, it'll be good. There is our function. Let's go ahead and find some patterns now. So we already talked about this before. Where does this 2 come from? Well, what happens in the table? Well, the 2 means I'm multiplying by 2 every single time. If I go backwards, I divide by 2. What that means is my heights here are multiplied by 2. Check it out. This height was 3, then I go to a height of 6, then I go to a height of 12, then I go to a height of 24. So in terms of the graph, I'm doubling each number. 3 doubles to 6, doubles to 12. Since I'm doubling, this base here, this factor must be 2. If I were tripling the heights, this factor, you guys would all shout out, is 3. So that's where the 2 comes from in the relationship between the equation and the graph. That's what I'm trying to get you to pair up. So the next question is, well, where did we get that 3 from? Does anyone see? Like, where did that 3 come into play? Yeah, Amy?
The 3 originated from x coordinate 0.
Whenever x is 0. And that's 100% of the time going to be where it comes from. Whenever x is 0, whenever I'm looking at where it crosses this y-axis, that is going to be this value right here. So what I'm going to do for our notes is I'm going to come and annotate, and I'm going to say, hey, this 3, that comes, and it's wherever I cross the y-axis. So I'm going to say cross y-axis. And I like the way Eamon said it too, which is it's wherever x is 0. So you can think of the 3 also right here, whenever x is 0.
So it's the y-intercept.
It's the y-intercept. Those are the only 2 numbers that you need to know for today. Eventually I'm going to make this more advanced and not too hard when you're in Algebra 1. In Algebra 2 they get really, really complicated. But for now, where does it cross the y-axis? That is your initial value, your number out front with no exponent. And then how much are you doubling, tripling? What are you doing in the heights? That's going to be your base number and then to the power of x. Every single time. You guys ready to try out your new math? All right, here we go. So we're going to graph this equation without using any table. Let's see if we can do it. I need help. What do I do?
Well, did you use this?
Let's use quiet raise hands. Yeah, what?
So first you're gonna want to graph the point where x equals 0. So for your power, you're gonna make that 0. So 4 times 1 is 4. So that's gonna be your first point.
Okay, so 4. I see 4s. Whatever. Where do I?
The y,
Oh.
y, because g times x is really just y.
Okay, so on the y-axis, graph the point 0, 4. All right. What's another point that I could graph then? Yeah, Jade.
1,8.
1, 8. How'd you get that?
I multiplied by 2.
Why'd you multiply by 2?
Because that's my next exponent.
It would be for your last equation, but for this equation, we're multiplying by something a little bit different. Do you see what it should be this time?
Oh! 4,16.
Not quite. What number should we be multiplying judging by this equation? We've already used up the 4. The 4 is used up in the initial equation, or in the initial point.
1,12.
There it is, 1, 12. How did you get that? That is correct.
I multiplied it by 3
And why'd you multiply it by 3?
because it's our x.
What is this, the name of this guy called? There's 2 names you have for it up your notes.
Base.
Base or?
Factor.
Perfect. Your factor is 3, your base is 3, therefore our heights are going to multiply by 3, and you can keep doing that over and over and over again. So 12 times 3 is 36. I come 2 and then up to 36, and now I'm off the chart. I can go backwards as well. I can divide by 3. So 4 divided by 3 is a little bit over 1, so I'm going to say right about there. And then we can't really graph any more points than that. We just know that it does get closer and closer to this x-axis the farther out left I go. So I can do this really close line that eventually comes up and through these points and then explodes off into infinity. It's Buzz Lightyear's favorite function. And there's our graph. And I'm going to circle the point so it's very apparent in the notes. You need to have those 3 points. This point out to the left you can't really graph very easily, but these 3 points, you have to be able to find those points every single time. So you might want to circle those as well. That's what you're going to be doing in Khan Academy. You're going to be checking 2 to 3 points, and they're usually the ones towards the right. Sometimes you'll have one on the left. All right, so now let's go backwards. Making an equation from a graph. How am I going to do this? I'll let you guys think about it for a sec. I'll give you a hint. Y equals, and there's your hint. Now you have to fill in the rest. Y equals, well, we have an initial value. We have our factor, our base, power of x. Okay, what are the heights multiplying by? What are the lattice points that this curve goes through? All right, Larissa, talk to us.
Well, since at the baseline it goes through 1, that would probably be the first.
What do you mean by baseline?
Like the y. intercept is 1.
Okay.
And then I was thinking since the next dot is at 1, 5, I think it would be like 1, 5. Or I'm not sure actually. I don't really know.
1 times 5, you're just missing a little bit. Look at your previous equations on your notes too. Where does x go? Right here?
No, to the power of x.
Power of x? Done. Answer. Question, Esha. Yep, that's it.
So the reason that Jade, so this is going to the last problem.
Yes.
The reason Jade multiplied by 3 is because it's 4 times 3 to the power of x,
Yeah.
correct?
Yep, so this 3, that's the heights are being multiplied.
So that's how, so by looking at the equation, we can automatically figure out what we're going to need to multiply by.
Exactly.
Okay. Okay, now I understand.
Yeah, and then Larissa, your equation is not going to look like that quite on Khan Academy because 1 times anything is itself. So very frequently this is going to be looking like y equals just 5 to the power of x. They're both the same exact answer though. This one is a little bit more simplified. Yeah, good job. Are there any questions on how Larissa did that last example, making an equation from a graph? Yep. Now, so I've been making this too hard on you guys now. This is what it looks like on Khan Academy. It's a little bit easier. It's multiple choice.
Oh.
And so I've been scaling my axes to make them look easier. Khan Academy doesn't do that. They give you like a nice tidy little 1x1 not scaled axis. So you only get like 1 or 2 points to even check. So there's your function, example 1. You can move on to example 2 and you can move on to the homework if you think you know what you're doing. But definitely everyone needs to have at least example 1 done with the next few minutes here. So try it out.
Hello everybody, Professor Wyatt here. We're gonna solve this equation. So if we go back to our notes above, we can see that this 3 right here is the y-intercept. So if we come back down here, then we know that this 2 is the y-intercept as well. So it either has to be B or C because D and A don't have the y-intercept of 2. And then if we go back over here and we plug in 1 for x, so if x equals 1, then 2 times 4 to the 1 is 2 times 4, which is 8. So the next point it must go through is 1, 8. B goes through 1, 8. Your answer is B. Thank you for listening in. This has been Wyatt.
So for example 2, we have the y, oh shoot. Okay, well the y-intercept is 1, so it has to be either one of these two. And then it goes up by, so then 2 to the power of 1 is 2, so 2 times 1 is 2. So it should, oh wait, so it can't be that one because it would have to go through 2, and 1 times 3 is 3, so it is B.